But I think today, this is our first keynote in the digital form because we already have a Beijing opening, and Dr. Li Feifei Li gave a Beijing keynote in the face-to-face opening session yesterday. But today is what I call the digital opening, and we have very fortunate. We've been very fortunate to have our opening keynote in this session. So now it's my honorable duty and my privilege to introduce our opening keynote, Professor David Harel. Professor David Harel has been at the Weizmann Institute of Science since 1980. He served in the past as the Dean of the Faculty of Mathematics and Computer Science. He is currently also the Vice President of the Israel Academy of Sciences and Humanities. He has worked in logic and computability, software and systems engineering, modeling of biological systems, and the topic today, odor reproduction, and many more other areas. He invented the state charts and co-invented the life sequence charts. I remember when I was still a student, I have to study state chart. That is definitely a very powerful representation of the system state. And he also wrote many books, such as the algorithmics, the spirit of computing, the computers published by Computers Limited. Well, another book is Computers Limited, what they really cannot do, and some other books. His many awards, including the ACM, Carlstrom Outstanding Educator Award, the Israel Prize, the ACM Software System Award, the EMET Prize, and he received 5 honorary degrees. He is a fellow of ACM, the IEEE, the AAAS, and the EATCS. He's a member of the Academia Europa and the Israel Academy of Science and Humanities. He's a foreign member of the U.S. National Academy of Engineering, the National Academy of Arts and Sciences, and the U.S. National Academy of Sciences. He's also a fellow of the Royal Society. Now, without further ado, allow me to present our keynote speaker, Professor David Harel. David?
For both the invitation and the kind introduction, which in my opinion was a little bit too long. You could have cut that down to say less things, but let's go along with that. So I'm going to talk about odor reproduction and how to test for it. And first of all, I'd like to ask a question of the audience. I cannot see the audience or receive responses, but let me just give you a few seconds to look at this picture and let me know, well, let yourselves know if anyone has any idea what this is. So just a few seconds of dramatic pause here. So the answer is this is the first photograph ever taken. It was taken by Niepce around 1826 or 7. The original on some kind of metal plate still exists in some museum somewhere. And I must admit that when I first saw this picture, I was really emotionally excited, because this is really the first time that some scene has been captured by chemical or electronic means. Of course, people painted pictures for ages, but this is not a drawing or a painting. It's something that was captured by a click. Of course, it was a very long click. It didn't take 1/100th of a second. It took longer, but that's the story. Here's another picture. When I put this up, some people say, oh, if the previous one was the first photograph ever taken, then this is probably the second photograph ever taken. Well, no, that's not true. I hope you can see my mouse here. If you look down here, you will see there are 2 people here. One person is shining another person's shoes. So this is really the first photograph ever showing people. in a way, this is even more exciting because these two people down here are the first people whose image was captured, again, not by a painter or a sculptor, but by a photograph. And this was done about a decade later. Now, if we move from pictures, from views, from scenes, from video to audio, then exactly 50 years after Niepce, the first telephone call was made. This, of course, was done by Alexander Graham Bell. This, by the way, is not a picture of the first telephone call. I think this is a picture taken when he conducted the first transatlantic telephone call. But nevertheless, the story around the first telephone call is very famous. He put the device to his ear, another device to his mouth, and he said, he asked his assistant, who was in the other room, "Mr. Watson, could you please come here? I want you." And of course, the really amazing thing was not that he said these words, but that Watson came over. So that means that the voice was transmitted, was captured, transmitted properly. And Mr. Watson, of course, this is not the Watson of Sherlock Holmes. This is the Watson of Alexander Graham Bell. He came over. So these are two milestones in our ability to transmit, to capture and transmit scene and voice, audio and video to a remote place. And in this talk, I want to talk about exactly the same issue, but not using the sense of sight or of hearing, but using the sense of smell. So we want to talk about olfaction rather than about vision or audio. And so what do we want? Well, we want it to be the case that if we have something that has some odor, say a rose, we want to capture that odor with some electronic device, a chemical electronic device, whatever. This is the analogy to a camera. So if you keep in mind throughout the talk, the analogy between what I'm talking about and, for example, digital photography, camera, printer, printing a picture on a piece of paper, then you will be pretty well aligned with what I'm talking about. So here we have something which is really an odor camera. We will be calling this device the sniffer. Sniffer sniffs an odor, and it turns that odor into some kind of digital fingerprint, which of course, since it's digital, we can transmit it to any other location. And we want this digital fingerprint to be read in by some computer, endowed with some mathematics, computer programs, algorithmics, and so on. And we want this computer and its software to be able to give instructions to an output device, which is like a printer. We will be calling this device the whiffer, because it's going to whiff out molecules. And we want the property of this cycle to be such that the input odor captured by the sniffer, when transmitted to the computer, who gives instructions to the whiffer, the output device, will emit molecules, because molecules are the only way human beings and mammals can smell, such that those molecules, this is an audio effect here. So we want it to be the case that the molecules emitted by the whiffer, when sniffed by an average human being, will cause that human being the feeling that he or she, in this case it's a he, of course, is smelling the original rose. Now, so what we're doing here is some kind of imitation of the input odor. So when I put up the slide, I like to say that what we see here is we want the rose to be posed in our nose as a rose. We want the rose to pose in our nose as a rose. And the most important word in that amusing kind of sentence is the word pose, because just like if I take a picture with a digital camera, I happen to be an amateur photographer. I have a very expensive camera and several expensive lenses. And if I take a picture of this room over here, and there is something with a particular color, and then I give it to my digital printer to print, that color will come out on the piece of paper or maybe on the screen, almost exactly the same as the original color, maybe not 100%, but it's sufficiently close so that someone who looks at the picture will say, aha, this is a picture of David Harel's living room, and all the colors are okay, and all the shapes are okay. This is what we want. We don't necessarily want these molecules to be the exact same molecules emitted from the rose. That would be impossible, because otherwise this device would have to have all the molecules and all the combinations of molecules in the world, but we want it to act like my printer, which has, I think, 4 different colors of ink, but it mixes them in a clever way in order to give the correct color, which is close enough to the original color. The same here. And another important thing to say about this picture here is that this odor reproduction system obviously must be able to work for any possible odor. Those that you can talk about and describe, such as, you know, coffee with cardamom, or orange juice, or pizza, including those you cannot describe in words, such as the odor in my grandmother's attic, for example, and also including odors that none of you, not me and not you, have ever experienced, such as, you know, if we go to a remote jungle in South America and we encounter a crazy giraffe that no one has ever seen, a purple giraffe with yellow stripes, and we smell that giraffe, or we smell its armpit or whatever, and this is an odor that no one has ever experienced. We want that odor also to be reproduced in a reasonable, recognizable way by the system. So this is very important, because you will never buy.
Professor Harel, we cannot see your entire screen. Could you reshare the screen?
Oh, I was
just reshare it and bring back to that slide. I think it's a little bit off.
Okay. Is this okay?
The backstage, is that showing properly or not?
Can you see this now, Carl?
Not yet.
I don't understand this, because I just did share screen.
Share. Can you share the entire screen? When you do the share screen, that says the entire screen.
Is this okay now?
It's cut off on the right hand side. I don't know why it's not showing the not fully on. So share the entire screen when you. Oh, yeah, this is the entire screen.
So I should make this larger? Is that what you're saying?
No, this is okay. And should we keep this way on the backstage? This is fine.
This is fine. Okay. So such a system would have numerous applications. Of course, you know, TV programs where besides seeing and hearing, you can also smell what's going on. I'm just closing a window here. Sorry. Cooking programs, online purchasing. I often buy flowers for my friends online. I get to see the flowers, I get to pay for the flowers, but I don't get to smell them. And I have several members of my family who enjoy cooking programs vastly. I can understand that, but I really cannot share the excitement by just seeing someone cooking or baking on the screen and hearing the sizzling and the noises, but not being able to taste or to smell what is happening there. Computer games, medical diagnosis. I had a friend, he passed away a couple of years ago, who was a doctor, a pediatrician, and he had the uncanny ability to detect streptococcus from a child's breath. He could smell the breath on a baby and tell with very high accuracy if that baby had streptococcus in their throat. And of course, there are entire industries, such as the food and cosmetic industries, which are deeply dependent on the ability to taste or to smell. And just as a side remark, I hope that you in the audience are familiar with the fact that most of what we taste is really what we smell. Our tongue can detect, sweet and sour and bitter and a couple of other facets of taste, but most of the experience of tasting something comes from the fact that the molecules even when we eat, go up our nasal cavity into the nose and we smell. So it would really be wonderful if we were able to transmit a cooking program such as Master Chef or Master Baker in real time with odor. So you sit on your living room couch, you have maybe a little device here, which looks a little bit like a microphone. And as you're viewing this program, this device, this whiffer, emits tiny, tiny quantities of molecules to match what is being seen on the screen. And that would be really wonderful. And I can tell you from experience with several toy examples that we carried out some years ago, that the experience of viewing something on a screen and hearing it and also smelling what's going on is an unbelievable experience that I find it hard to convey to you without you actually experiencing. Another comment is that it's sufficient to have a very tiny quantity of molecules. If you want to smell coffee, you don't need an enormous enormous cloud of coffee odor in your face. You just need a tiny quantity which gives enough to experience the magnificence of seeing, hearing, and smelling at the same time. So why has it taken so long for this problem to be solved? It has not been solved yet. We're in 2020, almost 2021, and I would guess that we're still between 3 and 10 years away from having even a very crude system for odor reproduction. Why is this much harder than for sight and sound, which, as we saw earlier, the problem, at least in very primitive resolution, was solved already at the beginning and at the middle of the 19th century? And I think the answer should be obvious. Sight and sound are waves, and not an odor is molecules. So we understand the mathematics of going from a wavelength to giving instructions to a printer to mimic that wavelength, or from a wavelength for audio to giving instructions to a loudspeaker to vibrate and mimic that wavelength. We know what a Fourier transform is, we know what an inverse Fourier transform is, but molecules, I mean, how on earth, by sniffing some set of molecules, some odor, using a sniffer device, how on earth are we to give instructions to an output device that has a certain number of molecules in it to mix those molecules in order to mimic any possible input odor? I'm going to skip this. You can read about the human olfactory system on your own. I won't explain much, except to remark that our olfactory system, and that of mammals in general, has several hundred different types of olfactory receptors. So unlike what happens in our eye for vision, there is a large number of receptors for olfaction, and what the brain, the upper part of the brain, receives from our nose when we sniff something into our nose is a combination of several hundred signals coming from several hundred different types of receptors, which is one of the reasons why this is a very complicated kind of encoding. But I'm not going to talk about the biology or the chemistry. I think I will also skip this. This was an April 1 joke that appeared in 2013, where Google made fun of having the ability to sniff. During that day, you could enter Google and you would see something like this, and it said people also sniffed orange juice, garlic. And the fact that this was a joke also is a evidence of the fact that even Google at the time realized that this was a difficult problem. And I want to press that point of building an odor reproduction system being a very difficult scientific and engineering problem by stating which areas of human knowledge and human research have to be involved in solving this problem. And it's quite remarkable. You need chemistry because we're talking about molecules. You need electronics if you want to emit certain numbers of molecules accurately given a prompt in small quantities. You need physics, you need brain science to understand what the brain does. You need engineering. Think even about the material that you have to use for the pipe that leads these molecules to be emitted in front of you. If you use a material that kind of gets contaminated by certain molecules, then after you've emitted a few different odors, the next time the orange juice gets mixed up with the coffee gets mixed up with the mud, and the whole thing gets confused. So even engineering the system using the right kind of materials is difficult. You need psychophysics if you want to understand not only what the brain does with the signals it receives from our nose, but what the perception of odor is for human beings. You have to understand that also, because the brain over here might receive from the electronics a certain combination of signals from our nose, and if you might have two odors which have similar looking brain signals, but their perception in our mind is very different, and vice versa. You might have signals that look very different, but our psychophysical perception is very much the same. And of course, because I'm a computer scientist and a mathematician, for me the most interesting thing is, what do mathematics and computer science have to do with this? I'll say a few words about that a little later on. Let me say first something about the two pieces of hardware. The camera, the odor camera, which we will call, as I said, the sniffer. So this is a device that maps molecules into vectors of numbers. So you have an odor, you have the sniffer device, and you get some kind of, for odorant O with concentration C, you get something in the sniffer space, which is a vector of numbers. How these vectors are produced, of course, depends very much on the sensors in this device. I'll show you an example of a couple of examples of these sniffers very soon. The properties, these are really exist. Such devices exist. They're called electronic noses. Some of them are very large and very expensive. They're used in very many industries. Some of them cost $150,000. The cheap ones cost less, but they're not very cheap. But what is done using electronic noses in industry is extremely modest, humble, primitive compared to what I want to do with them. And just to press this point further, most of the usages of electronic noses in industry are to make a binary decision. Is this cheese okay, or has it gone off? We once, does this package carry a bomb or some explosives, or does it not? I was once talking to people from Nestle, chocolate, coffee chocolate company, and they were using electronic noses to test different kinds of paper in which they wanted to wrap some candy, either Kit Kat or Bounty or Mars or something, and they wanted to know whether this particular kind of paper, if you wrapped this candy bar and left it for 2 months, whether it would influence the taste, which, as I said, is really the smell of the candy bar 2 months later. Again, this is a binary decision. Just to compare to photography, try to imagine that photography had never been invented. And here I come along, David, in the 2020 conference that you have just invited me to, and I come along and I say, hey, dear audience, I've just invented photography. And you say, okay, show us. And I wheel in an enormous device that costs $200,000, and I point it at the, say at the lecture hall, and I go click, and the device is able to tell me whether there is more light in the lecture hall than outside in the corridor. A binary decision. Or maybe whether the average color is a warm color, red, orangey, more so than the blues and greens, the cold colors outside in the corridor. This is a binary decision. This will be absurd, of course, but this is what you do with electronic noses. I want to use electronic noses to do the analogy for odor of taking a photograph and recognizing that this is a lecture hall, or this is the living room, or this is the jungle. And so in that sense, we want to use electronic noses very much more smartly than they are used today. What about the printer, the whiffer? So the whiffer has to have a palette of certain basic odorants, just like I have 4 colors of ink in my in my jet ink printer. Laser printers work differently, of course. Experts on olfaction estimate that it should be possible to choose about between 50 and 100 carefully chosen odors, such that if you could combine them with single percent resolutions, so give me 16% of this, 0% of that, 3% of that, 1% of that, 71% of that. If you can mix them with a single digit percentage resolution, then you can span the entire spectrum of all odors that human beings can discern. As I said earlier, we want to control the release in very, very tiny quantities, but accurately in terms of timing. So if you see a movie and the police are running after the thieves, and they're driving and they take a sharp turn and you hear the tires screeching on the road, you want to be able to smell the burnt tires, but a couple of seconds later you want to smell something completely different because the scene has changed. So basic odorants plus this whiffer device itself give you the ability to emit these molecules. In order to deal with a question that I'm always asked here about basic odors. People ask me, is there RGB, red, green, blue, for odors? No, but as I said, it is a belief, a general belief, that you can span the entire space of recognizable odors, at least to human beings, with a carefully chosen basis of 50 plus odorants. Now, I was involved in 2001 and 2002 in a company where we were planning to try to solve this big problem, but we were also hoping to make money from much more modest applications, such as, so I remember we were building a set of 3 computer games which also had an odor channel. We had a wonderful whiffer, which was supposed to look like this with various colors. It had the ability to hold 60 or so odorants and release mixtures of them. Of course, we did not solve the big problem, which I'll get to in a moment, but we were planning to market computer games with an odor truck where you release pre-arranged odors at particular places during the game, including one game where we used odors not only to enhance the pleasure from playing the game, but also as part of the strategy. I remember one of the games, the story was that the princess was kidnapped at the beginning of the game, and right at the end, if you passed all the stages and you were about to win and release the princess, you find yourself in front of 3 closed doors, locked doors. You have only enough strength left to break one of the doors open, and you have to choose the right door. And the way to finish the game was to press the odor button and to sniff what you smell behind the doors. And if you detect the perfume that the princess had at the beginning of the game and you remembered it, and you pressed the door with the right perfume, then you get to win the game. This company collapsed in the spring of 2002 when the entire high-tech bubble burst, and since then this has not been revived. But our plan was to make money out of simple applications, but also to put a lot of effort into solving the big problem. But the most important part of this entire talk is to try to explain to you why building a sniffer, and as I said, sniffers exist, they are expensive and they're large, but they can probably be made smaller and cheaper, electronic noses. And we built a wonderful whiffer, and there are other whiffers out there, other odor emitters and mixers out there. Building these 2 devices is not a big problem. That's the easy part of the problem. The difficult part is not buying a camera and buying a printer, but having the ability of the camera or of the computer to send instructions to the printer as to how to mix the inks. And this is the difficult part here. How to find a way to use the digital signature of an odor given by an electronic nose to instruct the whiffer to mix its basic odors in order to satisfactorily and adequately mimic any input odor. How? In a way that is recognizable by humans, and we'll get to that towards the end of this talk, using their real-world experience. And as I said a couple of times, for image and for sound, this problem was solved years ago, and our ability, technical and scientific abilities, are only getting better and better. I told you already that I'm an avid amateur photographer with a fetish for expensive equipment, and I'm pretty sure that in 5 years' time I will probably want to replace my camera and some of my lenses by even better ones, but that's not the issue. The issue was that in 1826 and in 1876, these two problems, in a very basic way, but in a profound, impressive, revolutionary way, was already solved very early on. And it was already obvious then that these breakthroughs are such that once we have internet, then we can also reproduce anywhere in the world and communicate them remotely. What does someone like me have to do with any of this? So first of all the work I've done on this problem, and this is only about 15 or 20% of my research. This is not what I do most of my work on, but still I have done work on this and still am involved in this problem. What do I do? And so first of all, I always work with an expert on olfaction. Lately, it has been someone on in our institute from the neurobiology department by the name of Noam Sobel. You'll see his name in a few minutes. But the short answer to this question is that, among other things, you need computer algorithmics and mathematicians to try to find mappings, correlations between the various odor spaces relevant to this problem. We've mentioned some of these spaces already. We have the eNose output. The eNose output is a vector of numbers. If you have a particular eNose, you have a space of vectors of a certain dimension. Molecular properties. Odors are molecules, mixtures of molecules. Each molecule has thousands of different properties. Which atoms sit where, how is the arrangement, how is the folding, what receptors do they have, and what do they emit, and so on. We spoke briefly about the brain response. These several hundred receptors pass several hundred signals to the brain. The brain does something with that. And of course, the most elusive of these spaces is the way we're perceived, human beings are perceived. And for example, how do you map an eNose output to the brain response? Or how from the brain response can you somehow predict perception? Or how from the molecular properties you can figure out how the brain will respond? All these are problems of mappings between these spaces, and you have to map, because if you want to go from an eNose output to human perception, you have to be able to touch upon these spaces. And very, very briefly, I want to show you some of the results I've been involved in, and then leave about 10 or 12 minutes to pose a much more modest problem than the big holy grail problem of building an odor reproduction system, and pose it to you and also show you how I propose to solve it. So I'm going to go through some of our results. So I had about 10, 15 years ago, 2 electronic noses that I was able to purchase. One was called Moses 2. It cost about $70,000. I was able to buy it for various reasons that had to do with a certain company going bankrupt. I bought it for $7,000 for my research. This is the device itself. It's connected to a computer and to a sampler where you give it certain chemicals, and it reads the headspace of the top of these liquids. And I also had a much cheaper and much less accurate handheld electronic nose that cost about 1/10 of the previous one. This electronic nose, by the way, had polymer sensors. The previous one had metal oxide sensors and another kind of sensors, had 16 of them. This was a lot more accurate than that. And what are some of the things that I was able to do, or we were able to do? One of our main results from 2003 was the ability to predict the behavior of certain kinds of mixtures. We did this many times, not hundreds or thousands of times, but enough times to be able to say that as a feasibility test, it is feasible to try to build algorithms that, given, say, 2 odorants, will be able to predict what their mixtures will be like as electronic nose results. So let me explain this picture. This is a 2-dimensional plot of a 16-dimensional set of results. This is done using PCA, if you're familiar with it. What you see up here are 6 or 7 separate sniffings of a particular odorant with increasing concentrations. So this is one set of settings for a particular concentration, another one. As the concentration gets higher, the sniffings are not as good as they are down here, but they're still pretty good. And what you see here, which is interesting, of course, is a linearity in the way the concentration gives a signal from the electronic nose. This is odorant number 2 in dark blue. Again, several clusters of sniffings. Of course, I hope you realize that the reason these don't come out exactly one on top of each other is because it's chemistry, and each time you sniff something using an electronic chemical device, the results are influenced by the time, by the air, by whatever, and they might be slightly different. But still, you see linearity in concentration. Over here, the first exciting thing to look at here is a 50% mixture of the light blue and the dark blue odorants. And again, you see that this is more or less halfway between the two, so you get a linear combination of the two. And the most exciting is that this dark red is a 75% mixture of this one with 25% of that one. So this is being pulled down 3/4 of the way, and again you see linearity. I must add that from a pure chemical point of view, we know that linearity does not always exist. In certain concentrations it does not exist at all. For certain chemicals it does not exist. But this was the first time we were able to show something reasonable in certain cases, certain examples of mixtures. We were also able to map not between perception and the molecules, not between molecules and electronic noses, but between our two different electronic noses. As I said, they are very different. One is more accurate, one is less accurate. One is based on metal oxide sensors, one is based on polymers. And what you see here is, I think, an interesting picture that shows what happens if you sniff something with electronic nose number 1. You use our algorithm to move from the space of this electronic nose to the space of this electronic nose, and you compare the result of this mapping to an actual sniffing using this electronic nose. The closer the actual sniffing comes from sniffing here and moving by our mathematics here, the closer these two results are, the better your mapping is. And so the circles are the actual sniffings over here. The diamonds are the sniffings plus the mapping. So here it is not very close, but it is still close enough to make the distinction with the others. But here and here and here and here, the mapping is very, very good. If I zoom into this area, you will see that some are really remarkably close. This one is not very successful because you might confuse this with that, but still, as a feasibility test done several times on several odorants with our two electronic noses, this is an encouraging illustration of the ability using hard work to carry out a mapping. This was done, as I said, between 17 and 18 years ago. 10 years ago, we were able to come up with a much more powerful result. And this was done with, I mentioned Noam Sobel from our institute, and a joint PhD student of ours, Rafi Haddad. A very complicated project. We were able to build an algorithm that had the ability to predict from an eNose output how pleasant a human being would say a particular odor was. We did this on a wide spectrum of odors. We carried out experiments with a wide spectrum of people from different backgrounds. We did this in Israel, so we had people from Western and from Eastern backgrounds, people who came from Ethiopia, for example, who have a different sense of smell in various ways. But it turns out that whether an odor is pleasant, and our grading here was pretty coarse. It was, I think it had 4 or 5 levels. Level 0, terrible smell. I would never go near this again. And level 4 or 5, this is like paradise. I would, search for this odor wherever I go. And it turns out that people are pretty consistent about pleasantness. And it also is the belief of people in the odor industry that pleasantness is one of the main axes of properties of odors, just like brightness, for example, is one of the main axes of sight, and loudness is one of the main axes of sound. And we were able to make a pretty good prediction. I think the percentage of accuracy was over 80%, so it's much better than random. And I think this still can be improved. So in a way, this is solving a very, very, very modest version of the odor reproduction problem. We're not able to reproduce odors, but we were able to reproduce the level of pleasantness, at least on a grade of 4 or 5 point grading, and an accuracy of over 80%. So this is a good step in the right direction. I also want to mention that a very recent piece of work which you've just completed and has been accepted for publication in Nature, which I cannot share the details of with you yet because it's still under embargo until publication, but I would recommend that you seek out this paper done also with Noam Sobel. The main person doing the work is Aaron Ravia, another joint PhD student of Noam Sobel and myself. And this is a very encouraging and also extremely complicated piece of work, which takes another step towards solving the big problem. But again, I still think that the problem is 3 to 10, maybe 5 to 10 or 5 to 12 years away, because it's still not easy at all. Having said that, I do want to make the following statement, and that is that although I'm giving you this talk, and although we're working hard on these results, and although I believe there's still a tremendous amount of work to be done before even a crude solution to the problem will be presented, it might be the case that as we are sitting here and I'm talking and you're listening, it might be the case that I don't know, Samsung or Microsoft or Google X, this problem is being worked on very, very extensively, and maybe tomorrow morning a first version of a solution will be presented. I will be very surprised, but of course I will take off my hat, especially if we're able to prove that these people have solved the problem even crudely. By the way, I keep saying a crude solution. What I mean by that is something analogous to Niepce's first photographs or Alexander Graham Bell's first telephone call. I mean, if Alexander Graham Bell, instead of saying, "Mr. Watson, can you please come here? I need you," if he were to play a very high note on a violin, maybe his device would not reproduce it properly and it wouldn't be understood on the other end. And the same will occur with odors. Maybe the first solution to this big problem will not be able to distinguish between different kinds of red wine. That's okay, as long as it can say this is red wine and not whiskey, or not white wine, or not liqueur, or not coffee. That's good enough for a first step solution. And now I'd like to go to my final 10 or 12 minutes in which I would like to pose a thought experiment, which is closely related to this talk, and in particular, it's closely related to what I just said, that maybe very soon someone will come up with a proposal for a solution to the problem. And I'd like to pose this question and also pose a possible solution. When I give this piece of the lecture in front of a live audience, I give them a few minutes to think about it and to try to come up with proposals. The proposal I will make to solve this problem, I made it a few years ago. I published it in a paper. You can find it pretty easily, but it's not the only possible solution. I've heard somewhat different ideas from people, and it would be interesting to see if you can come up with some. But the question, I think, is extremely interesting, and what is nice about it, in order to solve it, you don't need to know any deep mathematics. You don't have to be a chemist or an odor expert. You don't have to have money for expensive equipment or PhD students and postdocs. You just really have to use common sense, which is what I used for about a year thinking about this problem. And I'm sure if you thought about it for long enough, you would come up with a solution. So here's the question. The question is, suppose someone, say Carl Chang, who you saw on the screen here more than once, also introduced me kindly, too kindly. Suppose Carl, if I may use him as an example, comes along and claims that he solved the problem. And he comes along and with two devices, he says, here, lo and behold, this is my sniffer, here is my whiffer, test me. How do we test? How do we convince ourselves that Carl Chang deserves the Nobel Prize for solving this problem, or deserves a lot of money because he also has a patent on it, or maybe he has not solved the problem and we say to him, dear Carl, we like you very much, but please go back and come up with a better solution because you haven't solved the problem. Now, let me remind you, or let me state that if you were in the room with Niepce in 1826, and he said, hey, I've solved the photography problem. It wasn't called photography then. Here, I just took this thing and I clicked from the window, and look, here's this picture, one I showed you at the beginning of the lecture. And you look at it and you say, did you paint that? Did you draw? He says, no, 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 I went click. You say to him, just do this again, maybe from the other window. And he goes click. It's a long click and he needs some chemicals to, to produce this metal plate. But then when you see the picture, you look out of the window, you say, hey, gee, problem solved. You don't say to him, I don't believe you. Come over to my house and I want you to do this 1,000 times. You believe it. Alexander Graham Bell called his assistant and he came along, and you see that this was done, and you and you say, maybe just do this for someone you don't know ahead of time. You see this once or twice, that's it. You don't have to ask yourself, well, maybe if instead of asking Watson to come along, he would have said, Mr. Watson, can you tell me what is the time? Then it doesn't work. No, you see one or two examples, that's it. But here, maybe Carl Chang, who is a very smart person, I can't see your face here, I hope you're smiling, Carl. He's a smart person. Maybe he says, I know what these people are going to ask me. They're going to try to test orange juice and coffee and pizza. So I will prepare, 10 or 20 of these, toothpaste maybe, that these people are going to try. And, I ahead of time, I know which ones these are going to be, and I haven't really solved the problem. Let's see if I can fool them. Think about this problem. It's not that simple. So what method of testing can we use that as we use it more and more often, our belief that Carl Chang has indeed solved this problem, or whoever else comes along with a candidate solution, has indeed solved this problem. It's not foolproof because accuracy, complete accuracy is out of the question. But how do we know that this is a solution that we believe, or we get ourselves to believe very strongly after working on this for a few hours, that the problem has been solved? Let me skip this transparency just to say what the main problems are. The main problems are the following. The first one I mentioned briefly earlier. In general, you cannot devise a testing method which asks people to tell you what they have just smelled. And then we ask Carl to reproduce, because as I said, you can describe coffee, maybe you can describe red wine, but you cannot describe my grandmother's attic. Most of us cannot describe, 95% of the things that we smell, we cannot describe in words so that someone else gets a good feeling for what it is that we are smelling and what the smell really is. So verbalizing odors is in general impossible. So a solution that asks people to talk, to describe, is out of the question. The other thing we have to take into account, as I said earlier, perfect imitation is even my expensive camera and lenses and a very, very, very front of line printer will not completely perfectly imitate a scene, and even a very good audio system will never perfectly imitate a good concert hall. So this we don't even have for image and sound. How do we solve the problem? And I'm going to describe my proposed solution. As I said, you can read the paper about it and find it easily. And it is based on two ideas. One, I think, is a pretty profound and idea which is important for this area. It's crucial to this area. And the other one is a technical thing that I will cover. Let me skip this also. So the key idea in this proposal is that when we smell something and we can't talk, we can't say what we smell, but we recognize it because it's immersed in something that we see and hear. In the real world, even if it's my grandmother's attic or the armpit of a purple giraffe in the Amazon jungle, if you are there and you see the giraffe, you can very well say, this is probably the odor of that giraffe and not of the coffee I'm holding in my hand. So that's the key idea. And what we do is we appoint two teams of people, a challenging team and a testing team. This word tester should be underlined here. So we have a team of challengers and a team of testers. And the challenger people, their role is to try to shoot down Carl Chang's proposal. They're like a prosecutor. They want to do all they can to convince a judge that Carl Chang has not solved the problem. The tester team are really the judges. They are impartial. They have no vested interest in whether Carl has succeeded or not. They want the truth. The Supreme Court, testing team is the Supreme Court in a good country which has a good Supreme Court. And so the challenger team, they take a month or a year. They go around the world with a video camera, with a microphone, and they choose any locations they want, and they produce, and they take Carl Chang's sniffer with them also, and they attach it to their video cam, and they take clips wherever they want, about 10 or 10 seconds long, hundreds of clips, thousands of clips, how many ever they want, wherever they want. They can go to the jungle, they can go to my grandmother's attic, they can go to a laboratory, they can go to a winemaker, they can go into a restaurant, they can go out into a meadow, whatever. They produce, say, several hundred or a couple of thousand clips. Each one has 4 inputs that they've captured. The video, the sound, I'm sorry, 3. The video, the sound, and they have sniffed the odor with Carl's electronic chemical sniffer. Now we sit the testing team in lineups. We give them 10, I don't think you have to read this, I will explain. You sit the testing team, each of them has a screen with 10 buttons, and they're given 10 clips from the challenging team prepared set of clips. These clips can be chosen at random, they can be chosen by the challenging team even, 10 clips, and they have one odor button. They can say, I'd like to now see clip number 3. No, please go back to clip number 1 again. Now clip number 6. Whenever they see a clip, they can hit the odor button, but they're only given one odor which matches one of the, say, 10 clips that they can see. So they have to say, just like in a lineup, when you're trying to figure out which is the person who stole your purse or which is the person who you just saw committing a murder, you have 10 clips, and you have to say which of these clips is the most fitting to fit this odor that you're given. Now, I'm not completely naive, so I realize that not every person will always hit correctly, but if you do this many times with many sets of 10 clips, and the tester team has several people in it, and you also use statistics to throw out outliers, people who always give wrong answers or give the same answer, use standard statistics. As you do this more and more often, and if the challenger team produces and asks for these clips to be in the lineup, then very quickly you become more and more convinced that Carl Chang has done his job and that he has actually solved the problem, even if some of the odors that you are asked to match with the clips in the lineup are ones that you have never ever smelled before, because you use your knowledge of the real world to say, this odor cannot be from a laboratory, this cannot be from a restaurant kitchen, this is definitely not screeching tires, oh, this must be David's grandmother's attic, and it smells a little musky, a little old, a little dusty. That's the kind of thing that you're able to do. So I think this is a nice way of carrying out such a test. And as I said, my belief is that if a tester team does this 10, 20 times on different sets of clips taken from a variety of clips prepared by the challenger team, very quickly we can pat Carl Chang on his back and say, great work you've done, you've solved the problem. However, there is a problem, there is a difficulty with this solution, which is given by this. You see, the challenger team might be overeager or even vicious. They might deliberately take their video camera to places where what you see and hear is completely different from what you smell. To give an example, they might go out to a very nice hillside with a very placid spring, a meadow with birds and flowers and rustling wind in the leaves, but they're standing right in front of a cave which emits a terribly nasty kind of bad smell. Or maybe they have just used their foot to tread on, excuse me, the excrement of some cows. Now, no objective, reasonable testing team will be able to tell that this placid meadow has this terrible smell. And it might be something quite different. In their pocket, they might have, some ammonia, something that has a very strong, has nothing to do with what you see. And if the challenger team are too eager to shoot down Carl Chang's proposal or vicious, they can ruin this testing process and choose cases where no testing team will ever be able to correctly point to the right clip for this odor. And here comes idea number 2, which is to make the test conditional. To understand this idea, you have to realize that it is possible today to capture the real molecules that exist here near these. So right here next to me, I have just happen to have some roses. I hope you can hear them. They smell very nice. And it is actually possible using laboratory equipment to capture the molecules of these roses and keep them closed for several days, maybe even several weeks, in a way that that when you open this vessel, you still have basically the actual molecules captured at the place. This, of course, will improve over time. And what we do here is the challenger team, when they go out to make their clips all over the world, they really take 4 devices. The lens that from the video camera that records the video, the microphone that records the sound, Carl Chang's sniffer that electronically records the odor and turns it into a digital fingerprint, and they also collect the actual molecules from the site, and they put a label on it where this was captured. And the idea for the test itself is very, very simple. Never, in order to glorify Carl Chang as having solved the problem by the testing team, you never require the testers to be able to do something for the artificially reproduced entity that Carl Chang's whiffer is giving them from what they are able to do with the original. So the lineup is conditional. What we do, again, don't read this, I will explain it. We split the tester team into 2 parts, testers number 1 and testers number 2. If you are on the tester team, you do not know if you're on team 1 or team 2. The only difference between them, all of them get these 10 clips at each lineup experiment, the 10 clips and 1 odor button. But the people from test 1, when they press their odor button, they get the actual molecules that you captured on the seed. Tester team number 2, when they press the odor button, they get what we had in the original lineup. They get the result of Carl Chang's whiffer, which maybe I didn't say explicitly. I hope you understood it 5 minutes ago, that the tester team in the previous version of the test gets Carl Chang's output. Now here, they all give their answers, which of the 10 clips they think is most appropriate that this odor came from. And we require, this is written here at the end of this piece, we only require that the people who are given Carl Chang's whiffer output succeed in identifying the right clip only whenever the people from team number 1 succeed in identifying the clip from the actual odor. So if the challenger team is vicious and they give cases where no one is able to tell, even in the real odors, then we don't require that from the device that Carl Chang has brought us and produces the artificial odors. And that's it. That is the test. And I think it's a subtle combination of human real-world recognition and imitation of smells inspired by photographs where, you see this photograph, of course, has been taken from this window, and I recognize the words that Alexander Graham then told me. It's also inspired by the Turing test for artificial intelligence, which I will not get into. Those of you who are familiar with it can tell the extension. And as I said implicitly, it gets around the two problems. It gets around the fact that we cannot generally name and verbalize and talk about odors so that you can recognize what I've just smelled. By using video and immersion, the testing, people don't have to say a word. All they have to do is point to the clip of which they think this odor came from. And it eliminates these unfair and vicious challenges by never requiring of the reproduced odor by Carl Chang's output devices, whiffer, that we do not already require of the original. I'll skip this, and I just want to close by saying that I hope that I have been able to do two things. One, at least, is to give you a feeling that there is a deep, very difficult scientific engineering problem that waits to be solved. It also has many, many applications. And also to give you this less deep, but also I think interesting issue about how to test such a solution. And I just want to end with an anecdote. When I wrote this paper on the testing proposal for this conditional video audio immersion lineup test, I submitted it to a very prestigious journal that you might be familiar with called Nature Methods, because I thought this was a method for testing something in science, in nature. And I got a very nice letter from the editor-in-chief saying, I really like your paper. I think the test is very clever, blah, 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 blah. But I cannot publish this in our journal without sending it to reviewers, by the way, because, she said, this is a method for testing a technology that does not yet exist, which of course is true. So I said, okay, and I went and I published it in another place called the Royal Society Interface. But the interesting point is that we still don't have full artificial intelligence technology, but Turing's test for artificial intelligence, which was published in 1950, by the way, the year of my birth, just so happens, and now we're in 2020, 70 years after his paper was published, we still don't have the technology, but Turing's test for artificial intelligence is extremely clever and has, as many of you know, has given rise to tons and tons of results, of thoughts, of criticism, of extensions, and so on. So I think that proposing a testing method for technology that is important, not as important, of course, as artificial intelligence, but to odor reproduction, even though the technology is not here yet, I think that proposing a testing method that we might be able to use if a candidate comes along next year or in 10 years, I think that's also pretty important. And I also hope that you appreciate the fact that this last part of my lecture, in order to come up with something like this, you really don't have to be a deep rocket scientist or a chemist or a mathematician or have lots of money for your research lab. It just takes some common sense. So thank you very much. And I think maybe I should stop my screen sharing now. Is that right?
Yes, I need to unmute myself. So thank you, Professor Harel, for your very informative, interesting, and intriguing talk. In the world of services computing, we have a phrase, a slogan. It says everything is a service. So today we heard from Professor Harel, smell as a service. That's very, very appropriate for this Congress. Now, thank you. Now I would like to open the floor for the questions, including the audience. I think some join us from China, from Asia Pacific, from different parts of the world, in different time zones. So also the main stage staff, you are also welcome to to ask Professor Harel some questions. Professor Harel, I actually heard this the second time. I heard your earlier version, and in this version, in the very beginning, you mentioned the application to the medical treatments, right? So, have you done those clinical tests, like people with Alzheimer's, and can we help them bring back some memories? And I think that can be very helpful.
Well, that's an excellent question. I mean, the general spirit of your question is excellent. Maybe I should say that I don't work on I don't work on applications at all. But there are several medical devices based on smell that work very nicely. In fact, I think there exists already a very good streptococcus detection device. And even the application you mentioned for Alzheimer's, there are devices that do a very good job on these. But I also want to say, to re-emphasize something I said during the talk, that these still are devices that make more or less binary decisions. Is this child sick, or is this child not sick? With Alzheimer's, it's a little more complicated. So I think these are wonderful achievements. The people who work on them have to work very hard on the engineering and the chemistry of this, but this is far from the general problem of reproducing any odor. I hope that distinction has been made clear.
Thank you. Thank you. Actually, another question is kind of related to the first question I asked. Is about a resolution. I heard that humans have some smell ability, and the dogs in particular, they can smell 2,000 different kinds of smells. Earlier, you mentioned about you think that 1% mixture will be enough, in your belief, to solve the rural problem. Why is not 0.1%? Why is 1%? And a dog can smell people with diabetes, with cancer cell, and so on. So those are amazing ability of the animals, of course. How do you compare to human ability, and why 1% is enough?
Well, first of all, the mathematics is that if you can mix at a resolution of 1% and you have 100 odors, you can do the calculation how many different combinations there are. It's an enormous number. And human beings can discern in the sense that, if you're given 3 odors and you're asked to tell which are the 2 closest, human beings can discern something like between 40 and 70,000 different smells only. So the mathematics says that maybe 1% is enough. But this is not a hard number. It's just something that people, not like me, people who really work on odor, seem to believe. And by the way, I want to again mention the name of Noam Sobel. I hope you've written this down, or maybe you can pick it up from my website. He is someone that I recommend anyone in the audience who is interested in this topic should go to his website and read some of his papers, not only the ones that he wrote with me, but he's worked on an amazing spectrum of issues between dogs and human beings. How people, for example, subconsciously use the odor that comes from tears. So let's say I'm talking to someone and the person is crying. The impact of the odor of the tears on the way I respond is something that they have looked into. So there's a large number of wonderful pieces of research that have been done, some of them done by Noam Sobel. And I always say this because many of the questions that I'm asked about this talk, I move them over to him because he's the expert on odor itself, including the issue of basic odors and how many do they need. I see here in the chat a question about mathematical tools for representation. We use many tools. None of them are particularly profound. I showed earlier that we use PCA to do a two-dimensional plotting of the results. The means that we use are pretty simple equations and procedures from applied mathematics. Nothing really to write home about. It's combining them together and using the data we collect from people, from experiments, and from electronic noses to put these algorithms together is the part that is difficult to carry out.
Right.
There's another question. Where can you find usage if you completed your duplication of a certain smell?
Applications, I think. Yeah, I think we pretty much already touched upon a few.
I'm sorry, I didn't get that.
I think he's talking about the usage. I think that's probably refers to application.
Oh, there are many applications. I mean, if you were to sit near my daughters here on the sofa and watch a cooking program, if they had a little device or maybe something coming out of the keyboard, and let me tell you a little story about 2002 in this company that we had a demo, we had a clip of an advertisement from Pizza Hut, and the clip showed a young, handsome couple walking into Pizza Hut and sitting down and ordering pizza and orange juice. And the waiter comes along with the orange juice, and a couple of minutes later, the waiter comes along with the pizza. Now, we had journalists and investors, potential investors, come to see what we were doing. And we told them that you have no idea what kind of experience it is to watch something and to hear it on a screen and to smell it. They said, okay, show us. We sat these people in front of this laptop, and we had this clumsy device, which we pre-programmed to emit orange juice molecules or molecules that smelled like orange juice the minute the waiter walks in with the orange juice, and then the pizza the minute the waiter comes along with the pizza. Now, all you had to do was to look at the faces of these people. They sat there, very skeptical, yeah, and then the music and then comes, and the couple walks in, they sit down, and they order. And then the waiter comes along with the orange juice. And then you see these people going, I don't believe it. I can smell the orange juice. And then a minute later, the waiter comes along with the pizza. And we program the system so that pizza is about 80% and the orange juice goes down to 20%. People almost fainted in awe, because suddenly you get to smell, you sit in an office, you get to smell real pizza, and you get to also smell the orange juice, which is on the side. All I can tell you is, and this is a very simple device, all you need is to emit. You don't need to solve the problem. You don't need to understand psychophysics, but you need to match what comes out of the sniffer, of the whiffer, with what you see on the screen. This is something we did very well, and the impact on a human being is remarkable. And which is why, if I were not a scientist and I were out to make money, and I recommend to you, found a company that sells even a simple device with 30 or 40 smells, but it is matched to computer games or to pre-recorded movies or something, and emits small quantities of these at a time. People will pay $150 just for the output device and the software, and you'll make a lot of money, I think. And then you can use that money to do even better things. I don't understand why such a product has not been marketed yet. I'm giving you free advice.
Thank you.
5% of the proceeds go to me.
Well, I hope soon, hope the pandemic can recede and I can travel to your lab and get a shock therapy on your lab. This is very interesting. I think it seems many of the dreams for computer scientists can be solved if we don't limit our imagination. Okay, so let me stretch a little bit here about a dream. Have you heard, since you're kind of in the reproduction area, have you heard of any dream reproduction? Have you talked to any neuroscientists through this kind of study?
About dreams?
Reproduction.
Real dreams.
I'm referring to like in the Old Testament, the prophet Daniel will be able to interpret dreams, but you have to be able to reproduce the dreams.
Yeah, well, before Daniel, there was Joseph. He interpreted the dreams of King Pharaoh from Egypt. Good question. I'm not an expert on this. I do know that there is a lot of work on brain readings while people are dreaming, what parts of the brain. And I think that if it's possible one day to decode changes in the brain in a way that you can see what's going on, I think it should be possible. I would not be surprised, by the way, if it's possible. So let me just go for a moment to a crude solution to what you're suggesting. I'm just thinking out loud. Let's say we don't want to reproduce a dream, but we want to say on a scale of 0 to 5 whether this is a nightmare or a paradise dream. Okay?
Okay.
I would not be surprised if this is possible. even with current technology. To tell by what goes on in someone's brain whether you're dreaming something that's very pleasant and you want it to continue, or whether you're going through a nightmare that you will do anything to get it to stop.
I think the difficulty for the brainwave analytics is that the individual brainwave are all different.
Yeah, but that's why I say I'm not saying that it can be solved today. I'm saying that it probably should be possible to discern from enough readings of enough brains what are the common properties, not of a dream about flying versus a dream about diving into water, but a nightmare and a pleasant dream. Maybe that can be captured and a prediction can be made.
We're just stretching our imagination here, I think, but it's fun. You have a third question here.
No, I just said that the human nose can differentiate tens of thousands of smells.
Tens of thousands.
Again, I have to say for the third time, we're not talking about smells that you can describe. We're talking about the ability to tell two smells apart.
Yeah.
And the easiest way to do that is you're given three smells, and you want to say that these two are taken from this hand, these two fingers are from this hand, and this finger is from the third hand. So given three smells, which two are different, more different than the other? And that is something that common knowledge among experts says that several tens of thousands of smells, 50, 60, 70,000 smells an average human being can tell apart.
Right.
There's of course the effect of getting tired. I mean, people can watch, especially during COVID-19 shutdown periods, they can watch television for hours and hours and hours and keep concentrating on the next episode of Star Wars or of Game of Thrones or of Handmaid's Tale. But if you smell something for hours and hours, somehow your sense of being able to tell what you're smelling gets dulled. This is something that we realize and will probably have to be taken into account when the technology appears.
Yeah, and our smelling ability is also varies between individuals.
Yes.
I can smell really well, but not my wife, because we're just different. Biologically, we're different. Yes.
By the way, it's interesting. I mentioned COVID-19, the corona virus. It's interesting that one of the most common symptoms of being infected by this virus is losing part of your sense of smell and taste.
Indeed.
One of my grandsons, who is young and strong, and it took him a few weeks to come out negative. He got the virus, and he was fine. He wasn't sick. He didn't feel bad, but he suddenly realized that he couldn't really taste and smell the food. He went and tested positive. Thank God he's young and healthy, and it went away after a few weeks. But that was his indication that he had contracted the virus. No smell, or very bad smell.
Well, so tomorrow we do have 3 sessions to do with the COVID-19. So here's the short commercial. Everybody please join the session. Let's talk about home office work during the pandemic.
Yeah.
Okay. I see actually there's no more questions on the any other question from the main stage.
That's okay. We don't have to have more questions. I mean,
right.
It's fine if there's none.
I'm just curious. I've always asked questions, so most of the questions from me. All right. So if no more, I don't see any more questions. So I think Professor Harel, I really thank you for accepting our invitation to give a very, very interesting, stimulating talk. And then I hope we can listen to you in the future. Hopefully, your sniffer and whiffer will come out soon, so we can really.
Maybe yours.
All right. So thank you. Well, if everybody we can hear you, just unmute yourself. Let's give Professor Harel a big applause. Thank you. All right. So, well, that was a great talk. Smell as a service. Okay, I can never imagine. I heard that last year, and it's just very intriguing. I think we do need to stretch our imagination, and because that is we are the researchers, and many of us are also the practitioners who would like to make things happen, and old dreams we would like to be able to realize. So I do want to very briefly announce that although we cannot have a reception and banquet, since we only can only meet virtually, I do want to invite you to the 2 plenary sessions. One is the awards session. It's going to is scheduled on Friday, and the TCSVC has many awards to be presented to the awardees this year. And that is for Friday highlight. And Saturday we have a concluding session. So I also would like to invite you back, and we'll have some announcement for the next year and the future plan. And take this opportunity, I would like to also call your attention that we begin to accept the hosting proposal for 2023. Our planning cycle is 3 years. And then with this, I think I would like to conclude this panel, and do come back, join us for all the many sessions. And thank you for your participation and your attention. With that, thank you all. Take care.